Hello everyone, my name is Wolfgang Schmidt. I'm the Sales and Support Representative for the PLS development tools in the Americas. Today I would like to provide you with an introduction in visualizing variables in an embedded application. This presentation will be based on an Infineon AURIX device, and you will see here the hardware setup that I'm currently using, which basically consists of an Infineon AURIX starter kit board and a U82 Pro device connected to the debug port of the controller. The presentation will cover the following topics: basic startup of UDE and navigation within UDE for our multi-core device, how to display global variable structures or single elements, creating real-time updates of a watch window, creating graphs for selected variables with multiple display options, and last but not least, the generation of data trays for fast-changing variables. Now I'm jumping right into the UDE, the Universal Debug Engine, which is how the graphical user interface from PLS is called. First thing that I will be doing is generating myself a workspace. I'm calling it Demo Embedded World 2021 Variable View. Once I have generated the workspace, I will select my target configuration. Under default, you will actually find a variety of default configuration files for pretty much all architectures that PLS supports. So that would be like a variety of ARM devices from different manufacturers, PowerPC devices or Infineon AURIX devices, just to name a few. For my specific case, I'm using the default configuration file for the AURIX2G, here in particular for the TC399. The AURIX2G is a multi-core device with 6 main cores, and I will be able to select which cores I actually want to debug during my debug session. Once I click OK, the debugger will start to connect to my controller and will load the interface to the selected device. Within the user interface, you will see the status for each core as well as the core color coding for the different cores. On the bottom of the screen, you can see which cores you are actually controlling, and this can be changed easily from one core to another. As a first step within my debug session, I will now load my application, or being more precise, I will load an L file that my compiler has generated and contains the binary as well as the reference to my source code. This opens up the multi-core program loader, where you can select into which core you would like to load your application. You can make selections for symbols as well as for the binary, and this is especially useful when loading different applications into the same controller. After confirming the core selection for the application to be loaded, it will detect automatically that the application needs to be loaded into the on-chip flash of the device. Within this dialog, you can also make additional changes for specific configuration blocks, such as the UCB for the AURIX devices. We are selecting the Program All feature, and we are therefore programming the flash right now, and once the load is complete, I can close all the dialog boxes. You also have the possibility to bypass all these dialogs and perform the programming automatically without any user interaction. Once I have completed this step, I will see my startup code of the controller, and I can simply perform a step over to skip debugging the startup code and end up in my main function. From here, I can simply set up breakpoints to any specific line and run to that particular point. I can now also use my symbol browser here on the left to open up a specific module where I will set a breakpoint and run to this specific function. At the top, I can see also that all the other cores have been initialized, are being stopped synchronously with the main controller. By activating the source window for core 1, I can see the current program counter for this specific core and the appropriate source code. You can do this also for all the other different cores. Once I am at this specific point of my application, I am usually interested in seeing the call stack to basically see the history of who has actually called this particular function. At the same time, I can also look at the local variables for each of the functions on the stack by opening the locals view. Within the core stack window, I can easily navigate between the different functions on the stack and also show the local variables for each of the functions. Since this is a multi-core device, I can also simply switch to a different core and show the core stack for this specific core. In the next step, we will be looking into the global variables using a watch window. First, I will be closing the core stack and the locals view to make it a bit easier to follow. Within the watch window, I can browse for my variables, and in this particular case, I will be adding a structure which has a variety of variables included. In the symbol browser, I can set up a filter for parts of the variable name. In this case, I will be using the structure g_updata. I can now open the structure and look for the elements within the structure that are of interest for me. In this instance, I'm actually interested in the structures counter data, time data, and calc data. And I'm basically selecting those and adding them as new entries, so I only have those substructures available in my view. The remaining main structure, g_updata, I can now delete. I will also close a few more windows, so that gives us a little bit more space in our view. I can now set or actually run my processor to the breakpoints and basically see on how my variables are actually changing. In many cases, I'm interested in setting a breakpoint on a variable access, in particular a variable write access. So this can be easily accomplished by performing a right mouse click on a particular variable and select the break on write, as it's being shown over here. I can also set up more advanced breakpoints by using the right mouse click and basically select the break menu and edit this, which gives me like an additional dialog box where I can, for example, define a loop counter like I'm doing it for right now. So basically after the fifth time, the fifth time is write access, the controller will stop executing the code. I'm running the controller right now, and you will see that it will stop right after it has accessed this variable 5 times. So basically the counter is ending up at the value of 6. I can also set up additional conditions. For example, if the particular variable reaches a specific value, so that would be basically also in this enhanced breakpoint dialog for the variables. I'm basically setting it up in the way that if that variable reaches the value of 12, it should actually break. So that's actually the setting right now over here. And so let's see what's going to happen. And as expected, it stops exactly when that variable has the value of 12. And we can from there further analyze the application. In a lot of cases, we want to see the variables being updated while the controller is actually running. UDE offers the so-called refresh period, which can be defined for each variable. There's a refresh setting for when the controller is running and a second one for when the controller is halted. The minimal refresh period while running is 25 milliseconds, which is more or less what the human eye can actually observe. Once you have enabled the refresh period, this is indicated by this blue update sign next to the variable itself. We can see now how the variables are actually changing in real time, and we can also enable the real-time update for all the other variables that we have in our watch window. The next thing that I want to show you is actually that you can also add a second value format for each of the variables, and you can also add like a minimum maximum column, so you can kind of see where the what value range that your variable actually had. So this is actually been shown here, and I run the controller again, and you can basically see how all of those values are actually being updated. Next, I want to show you on how to represent variables in a graph window. For this, we will open up a time value chart. This comes up empty initially, and I can add a new signal that I want to show in this window. So we basically select a new signal and define a few parameters. In our case, we want to record the signal sine var and cos var, which are actually kind of waveforms. So first I define the basic parameters for the window, and then I will select the variable that I wanted to record, where I'm using the symbol browser and go for an expression. For the time value chart, you can get an update rate as low as 1 millisecond. As a next step, I will adjust the properties of my window. Here you can define the total time that is actually being shown in the graph. Here I will choose the total time of 1 minute, and then I will also adjust my y-axis to better represent the value that I'm looking into. Once I have adjusted my graph settings, I run my controller and I can observe the variable in my chart and verify that it's actually generating what I was hoping for. I can see now very nicely on how my sine wave builds up in the graph, and I basically get proof that my application is actually generating what I was looking for. So let's just run this for a little bit to see like a full picture of my graph. I'm adding now also a second graph. This one will be for our cosine variable. I will be using the same y-axis as for the already included sine wave. Again, I will browse for the variable and add it to my chart, and then run the controller again. So we can see very nicely that both signals are in a relationship that I want them to be. Now for my example, here it would also make sense to record the angle from my variable. This one will be then using its own y-axis, since the value range is expected to go from 0 to 360. So I am going to add another y-axis, which I call angle, and then browse again for the variable. Once this step is complete, I can run my controller again and observe all three variables together in my graph. In this graph, I can actually also hover over any point of the curves and get detailed statistics of the curve, such as minima, maxima, and average value. I also have the possibility to zoom into the graph for a more detailed display. We have now seen on how we can generate graphs for variables that can be read out and do not change more frequently than 1 millisecond. For signals that may change at much higher frequency, we have the possibility to use the data trace recording. The device that we are actually using has an embedded trace buffer, which we can configure and where we can record selected data transfer. The trace can be configured graphically using the Universal Emulation Configurator UEC from PLS. To get started, we will open up a trace window and configure the trace. I have prepared this setup for the UEC already and will only need to load this into my configurator. The UEC consists of several function blocks. The first one in its tricore consists of basically the trace size and the controller that we actually want to record. Then we generate the virtual signals for write access to the variables that we are interested in. Those variables can be chosen using the symbol browser. And then we have a combination of those two signals into a third virtual signal that is then actually being used once that signal becomes active to store the write address as well as the write data. And in parallel, we're going to trigger the trace and we turn some timestamps on. My controller is actually running and I just started the trace recording, and here I have already the trace recording. As we can see here, the distance between, let me just adjust the window. As we can see here, the distance between those different signals is somewhat in the range of like a few microseconds actually. So it's definitely a much higher frequency changing than the other signals that we looked at before. Now I can actually open up a data graph from the trace, and I'm doing this right now, and I will basically see the representation of the trace recording in a graph. And that graph is obviously in a much higher resolution than the signals that we had before. So that's like another way on how to show variables in a graph or in a different way depending on your application.